Much like the characters in Steinbeck's novella of Mice and Men, malaria parasites are looking for a place to call home. These parasites have marginally more success and set up shop inside red blood cells. In order to turn their new house into a dream home, the parasites commence with renovations. My project examines some of the parasites' renovations, starting with bringing in some kitchen staples, milk and butter, otherwise known as calcium and cholesterol. Because it can't make its own cholesterol, the parasite steals it from the host cell membrane. This cholesterol depletion can change the biophysical properties of the membrane and affects the activity of membrane proteins. Then the parasite brings in calcium. Most of it is stored inside the parasite and its little bubble, the parasitophorus vacuole. But I saw that some of the calcium ends up in the red blood cell cytoplasm, where it can activate a calcium-sensitive enzyme called scramblase. As hinted at in the name, this enzyme scrambles the phospholipids in the membrane. Red blood cells usually like to keep one particular lipid, phosphatidylserine, or PS, hidden on the inside of the cell. But when scramblase is activated, the PS ends up in the membrane's outer layer. However, there's a second enzyme involved, this one called flippase. This enzyme flips the PS back to the inside. So these two proteins are at war, one scrambling the PS out and one flipping it in. I found that the flippase protein is actually working faster in red blood cells with parasites than those without. So even though the PS is being sent out, it's being quickly ushered back in. But if I treat the cells with a compound called vanadate, which inhibits flippase and means they can no longer bring the PS back in, the PS stays out in more cells. So why should we care whether the PS is inside or out? Because when PS is on the outside, this acts as a recognition signal to monocytes. These immune cells can bind to the exposed lipid and engulf the cell. My data shows that if you serve up some red blood cells to monocytes, they'd much rather eat the infected ones than the uninfected ones. But if I treat the cells with vanadate, the same inhibitor I talked about earlier, the monocytes get even better at finding and eating the parasites. I use vanadate in the lab as a tool to investigate what happens when I interfere with the mechanisms regulating PS exposure. But vanadate doesn't have the pharmacological properties to be a malaria treatment, so it'll never show any potential as a drug candidate. But it acts as a proof of concept that interfering with this pathway, whether by interfering with calcium or cholesterol or scramblase or flippase, can make the parasites more susceptible to recognition by monocytes and thus boost the body's immune system to help fight malaria.